Yeah, that's what I tell people, to always read the answer, all the answers.
Because I think they would do it all. If you just blowing through it and see the card, yeah, that's it.
That's it. Numbering systems and codes. Or, I guess they need to turn the projector on. That would help a little bit. So some of this is going to be a review, guys, back from DC. Decimal numbering system, explain engineer notation, explain exponent, integer numbers, fractional numbers, real numbers. And also we need to add floating point numbers on there. Now where we're going to add that is that's what the PLC called. That's what every PLC programming language that I've ever dealt with refers to basically real numbers. They combine fractional numbers and real numbers into what they refer to floating point. That's in the PowerPoint. Describe the binary number system, convert decimal to binary, vice versa. We're not going to spend a lot of time on binary math because even in PLCs, these guys are computers, right? You understand that? And we don't have a binary math instruction as a part of our programming language. So the programming language, all the math, from our point of view, it's going to look like decimal. Hopefully you have that, but I'll show you I'll demonstrate some binary math to you. We'll look at a number system called the hexadecimal number system. A lot of times this is incorrectly referred to as hex, but most people in the computer trade, that's what they call it because it strips it down quite a bit. We'll look how to convert numbers between hexadecimal and binary, which is the main thing we'll look at. We'll look at hexadecimal to decimal. We don't use that often. Normally, if we need to go between hexadecimal and decimal, we use a calculator that has that capability. But you'll find out converting between binary and hexadecimal and binary and octal, these are two numbering systems. You'll find out that this is not hard. But going from octal to decimal or hexadecimal to decimal it's not easy. In fact, it takes some math, and if it takes a lot of math, you might as well, you got a calculator that does that for you, you might as well do it. But it doesn't make any sense to use a calculator to go from hex to binary to hex, or the octal number system. We're also going to look at codes. We talked a little bit about this already. We've got to be able, since the computer only recognizes ones and zeros, guys, and there's more than ones and zeros in the world, and we got to use a lot of codes. So we've got to be able to represent all text with this, punctuations with this, controls with this. So these are referred to as codes that we'll learn, or we'll look at. We're not going to learn any codes except for a code called binary coded decimal, which is pretty easy too. We're going to convert numbers between BCD, binary coded decimal. Most people refer to this as BCD. We'll look at the gray code number system, and we'll look at ASCII. The book refers to as talks about Hexadec, but they don't talk about Unicode, which is the primary alphanumeric code that we currently use. At least it hadn't. So this is what we do. Everybody hopefully understands this. So we deal with exponents. And exponents is made of two things. It's made up of what we refer to as a base. This would be a base of 8. Then how many times we multiply that number together. So if we had 8 to the 5th, it means to get the answer, we would multiply 8 times itself 5 times. And we use this so often that just about every scientific calculator I know of gives you the ability to do it. It's either your y to the x key or x to the y key. Are we okay? Any questions here? So 8 times 8 times 8 times 8 is 32,768. Now, last class I gave you a powers chart, right? Understand that? That in base 8 should be on there if you look at it. I don't know how far I came up with. So this is what we refer to as, we call it a base. When we talk about numbering systems, we're going to say it's a base 8, a base 10, a base 10 numbering system, a base 8 numbering system, a base 16 numbering system. And a base 2 numbering system. These are the numbering systems we're going to deal with. Okay? So a base 2 means we're going to use 2 raised to some power. A base 16, hexadecimal is, hex is 6, decimal is 10, so hexadecimal is a base 16 numbering system. Octal, of course, that's octal is 8, so that's the name we give to a base 8 number system. And binary, which usually refers to as 2, that's the name we give to our base 2 number system. We okay so far? So scientific notation, a way to scientists and engineers easily handle very large and very small numbers. Written in a form of some number. So we use this guy right here, right? So this is not 5.6 raised to the 7th power. This is 5.6 times what? 10 raised to the minus 7th power cubed. Okay. We have people that'll do that. They'll raise the number up to the power, right? You understand? Does that make sense? And of course, if we see a negative exponent, what does that mean? It means it's a fraction, right? You're right. If we go backwards, it tells us which way to move our decimal point. And if we see a positive exponent, it means that yeah, right? Okay. So rounding, we always have problems with people rounding, especially DC and AC. For some reason, people got in their mind, to round means you just drop a fraction. Y'all know that's not true, right? So to round, what's the rule for rounding? 5 and above, we round that digit up. And 5 and 4 and below, we round that digit down. And then if we come up here, we have a so let's don't use a 5 there. That's their whole number we're looking for. So normally, what do we do in DC? What was the rounding rule that we use in DC? To the third digit. The third digit to the third phrase. Once we converted engineering notation, round it to 3 decimal points. And why do y'all do that in DC? Yeah, because you're proving laws. You're proving Ohm's law. It's just like in DC, you measure all your resistors. You don't use a tolerance, you literally measure them, and when you do your calculation, you don't use the color-coded value, you use the measured value, because you're trying to prove laws. So the more you round, the more it's going to look like Ohm's law is not exactly accurate. I mean, in fact, it is. So in DC, you should have round to 3 decimal points after you converted to engineering notation. That's the rule. Then after that, when we get up into more advanced classes like AC, we reduce the amount of rounding that we use, usually 1 digit after you convert it, 1 fractional point after that. And we use the color-coded values. We don't use the measured values anymore. And what we say is, you understand now, your math is perfect, but our components are not, right? You understand? So you know that if you calculate 100.5673 and it measures 105, that it's okay. Because of why? Because of the rounding, and there's a 5% tolerance on all the resistors that we have, that most of y'all use. So if we had this number right here, 137.46935, what would this do? 137.47. So if we rounded this to 3 decimal points, what would we have? Yeah, so this would round up, this would round to a what? This would round this guy up to a what? Yeah, 5, and this would round this guy here with a 4, and then we could drop those, right? Everybody okay? But what happens is this goes to this would go to 6, right? Okay. Everybody okay? It was a 5 and it would go to a 6. Right? And I'm sorry, and this would still be a what? You're right, this would still be a 4 and this would still be a what? 3. Right? Everybody okay? I should have came up with another number. If we round this to a whole number, what would this go to? If we round it to 138. Yeah, 138. Y'all understand a whole number is what? Just that. Fractionals move decimal points to the right until one whole number is obtained. So what we do is so exponents, are you okay here? So what we do is we give exponents names, right? We call this, this is referred to as scientific notation. And this is referred to as, this is still something. We use something called engineer notation. What's engineer notation? Everything is by 2. Yeah, by 3. By 3s, we move in 3s, right? So in engineer notation, we move in what? 3s, right? Okay. Well, on the positive side, we go 1 digit, and we jump to what? 3, 6, 9. On the negative side, we do, but it's minus powers, right? Everybody okay? That makes sense? So if we use an engineer notation, we go from this guy, and we jump next to what? 0. And then we jump to what? Giga, and then tera, right? On the decimal side, on the negative side, we start off with 1 digit, and then we jump to what? Milli, nano, I'm sorry, micro, pico, nano, pico. I'm sorry, they started moving in 3s from here over there. Well, no, they went 0, 1, 2. They said 0, 1, so they put deca over here, right? They did the same thing. I'm sorry. You're right. A decimal number system, we call this a base 10. Now, when we talk about bases, if I say base 10, it tells us 2 different things. It tells us that we're using 10 raised to some power, but it also tells us the number of number of digits we have available for each number, right? For each location. So what's the 10 digits we have available for in the decimal? 0 through 9. 0 through 9, right? You understand? So base 8 is going to be 0 to 7, right? Base 2 is going to be 0 and 1, and then base 16. Okay, I'm off. Huh? I'm off. Well, when we talk about the base is going to tell us 2 something. So if I say this is base 10, and that means I'm going to raise this base to some power. Well, the base also tells you 2 things. It's going to tell you, okay, this is going to be 10 raised to some power, but decimal is what we call a base 10 numbering system. And we'll look at why we call that. So basically, in fact, we'll look at it now. What you learned in high school or elementary school, when you did weights, so every digit has a weight, right? Okay. Every digit has a weight. Now you learn this as what? Units. You learn this as what? Tens, hundreds, thousands. Yeah, but that's the way you learned it, but that's not the way number system works. This digit right here holds a weight of the base raised to the 0 power. Now any number raised to the 0 power is what?
Zero.
No.
No.
1.
Oh, it's,
Yeah, it's 1. No, any number raised to 0 power is 1. You can get your calculator out and do that, right? Now this would be 10 to the first, this would be 10 to the second, this would be 10 to the third, this would hold the weight of 10 to the fourth, and this would hold the weight of 10 to the fifth. This is the way number systems work. So if I was dealing with a binary number system, I already know that this holds a weight of 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, I'm jumping, 2 to the sixth, 2 to the seventh. A base 8 number system would hold weights of what? 8 to the 0, 8 to the first, 8 to the second. Now what we learned is we learned what 10 to the 0 was. So we call that units, and we say, okay, that would be 1 times 1, right? You understand? This guy here would hold a weight, we call it hundreds, so that, I mean, we call it 10, so it holds a weight of 2 times 10. Well, what's 10 to the first? Any number raised to the first power is itself. So this is the way numbering system works. So every numbering system holds a weight of the base raised to some power depending on where it's in the position of the number. But it also tells us how many combinations each digit can have. So what's our combinations? Well, there they are right there. Nope. Yeah, I'm sorry. Here's one more. How many combinations is that? 10. So base 2 will have 2 combinations, right? 0 and 1. Base 8 should have how many? 8 combinations, 0 through 7, right? Binary is going to have how many? 2, only zeros and ones. In base 16, we'll get there when we get there. It's actually 0 through F. So base, this is also called the radix, multiplies for the digit or number constructed of the number system. 10 is base 10. So what we do is we're going to deal with, we just looked at that. This is going to be 10 raised to what? 8. Raised to some power, depending on its position. No, this right here. That's the symbol for alpha. Why they decided to use that, I don't know. But if you look at the Greek alphabet, that's a symbol for alpha. Now, how do I know that? Yeah. Well, it's one of the specifications that we have on a transistor. We have 2. We have, and you notice in physics and in technology, they use a lot of Greek terms. So we have 1, we call it the gain of a transistor, is called the beta. So we use that term. So this would hold the weight of 10 to the 0. This would hold the weight of 10 to the first. This is technically referred to as the radix point. But normally we give it the name according to the base. So what do we usually call that point in the decimal number system? We usually call it the decimal point. In the binary number system, we'd call it the what? Binary point. So that we usually give it according to the base. Over on the fractional portion, this would be 10 to the minus 1, this would be 10 to the minus 2, and then it increases as we go toward the right. So the fractional portions will be raised to a minus power of the base. And what's one? This would be in minus powers. It's always the reciprocal. So this would be 1 over 10, and this would be 1 over 100. So we learned it at tenths and hundredths and thousands, right? So on the left-hand side of the radix point is the base raised to positive powers. On the right-hand side of the decimal point is the base raised to negative powers. But anytime you raise a number to a negative power, it just means take the reciprocal of it. And what's the reciprocal? 1 divided by a number. And we use it so much that scientific calculators have that key on there. Because what it's doing is it's giving us the inverse of the opposite, right? Are we okay? This makes sense. So y'all learn this as tenths, which is, you learn this as hundredths, thousands, but actually true life, it's actually the base raised to some power, depending on its position in the number, right? Are we okay? So here's some powers of 10. So any number raised to the 0 power is always 1. Any number raised to the first power is itself. So a lot of times people think, so this says, okay, so this would be 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth. We can keep going, right? On the other side is what? 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, 10 to the minus 4, minus 5, minus 6, minus 7, minus 8, minus 8, and we can keep going. And how far could we go? Technically, we can go to infinity, but sooner or later we're going to give up, right? And that's where rounding comes into play. Even your calculator gives it. Most calculators, if they display, most calculators display 10 digits. It actually calculates 13 digits, but it displays 10. It uses those 3 digits to figure out how to round, right? And you can get them out, by the way, if you drop off your whole number and just multiply your fraction by 1,000. You can actually see the numbers that your calculator calculates. Windows calculators are really, I don't know how many digits they do. So this is the way of representing numbers in what we call positional notation. So what we do is we take the digit, and then we use each digit and multiply it times the power. So over here we got 6,310. So what that means, this is going to be 0 times 10 to the first. So this is going to be 0 times 10 to the 0. This is going to be 1 times 10 to the first, 3 times 10 squared, and then 6 times 10 cubed. Which basically is nice, but what we need to do is we need to see what each one of these are actually worth, right? So notice the next thing they do, they take the powers and convert them over to the decimal numbers that they represent. Now what we're doing this for is we can learn to do this, and we can go between any base. So 6 times 10, so this guy holds the weight of what to the number? 6,000. 3 times 100, so the 3 holds the weight of 300, right? And 1 times 10, this holds the weight of 10. And of course, any number times 1 is that number. And then we add all these together, and then we come up with a number. Now what I'm going to do is, we're going to be this number right here. These digits right here will be legal in 3 different bases. So this number right here would be legal in decimal. It would be legal in octal. And it would be a legal number that's in hexadecimal. So what I'm going to start doing on my numbers to let you know what base we're dealing with is I'm going to put a little subscript under all my answers. And I'm going to put it right here. I'm going to put a little subscript. I'm going to put a little 10 down there, which means it tells you that this is a what number? It's a base 10 number. So now, before long, we're going to learn that just writing down 63110, unless we say convert the number to decimal, just to keep y'all from getting confused, I'm going to do that. This has nothing to do with the weight of the number. This is indicating what they. This will be a base 10 number. So I could come down and write 6310, and if I put a little right there, it says that's what. And it's a different weight. The number has a different weight, even though it appears the same. And that's the problem we have, is that we want to see numbers as decimal numbers. And why? Because, well, that's what we've learned our whole life. It might be easier. It wouldn't be easier for a computer. Computers don't know base 10. They know what? They know base 2. That's it. But a lot of times when our computer displays things, it displays them in decimal, right? Because all it's doing is turning on dots. So your calculator does not do decimal math. Your calculator does binary math. But it understands if it threw a bunch of ones and zeros up there, half of you wouldn't know that, right? So it just turns on the patterns of the decimal number that binary number represents. So computers do not do decimal math. They do binary math. Some of them has the ability to do BCD math because that's easy to convert over. So the fractional portion, so 0.813, this would represent what? Yeah, 8 to the minus 1 plus 1 to the minus 8 times 10 to the minus 1 plus 1 times 10 to the minus 2 plus 2 times 10 to the minus 3. Then what's the next thing they do? They take these and they convert them over to the actual decimal weight they hold. So they're taking the exponent and converting it over to the decimal weight they want they own, right? So this is the 8 times 0.1, 1 times 0.01, and 2 times 0.001. Then what do? Then we add them together, we do the math, add them together, and we'll come up with the decimal equivalent. Does that make sense? You say they're making something hard. But normally, decimal number, we don't do this. Why? Because if I see 8,192.8, I know the way to that number because I've dealt with the decimal number system all my life. Right? You understand that? So, but what Book is trying to show you, or what we're trying to show you, is we can use this procedure to go from any base over to decimal. Any questions so far? Really? Okay. Real numbers. So this is what we deal with a lot. We have weights that are both positive and negative. We have real numbers are consist of 2 parts. They can consist of an integer. What's an integer? Yeah, that's whole number. Good. And then it consists of a what? A fraction. Your PLC is going to refer to these as floating point numbers. We'll talk about that in a minute. Are we okay? Digits to the left, so digits to the left of the real number are integer numbers, and digits to the right of the decimal point or the radius point of fraction. This should be something y'all already understand, right? Integer numbers. Most people refer to these as whole numbers. PLCs are called integers. So we need to know that what an integer and a whole number is the same. Have weights that are positive powers of 10. So in integers are no 10 to the minus 1. The numbers can be, they don't have a fractional component, right? You understand that? And they can either be positive or negative. We're not talking about negative powers. We're talking about negative numbers, right? You know, so I could have a positive 100. So normally when we don't see that symbol right there, we assume the number is positive, right? And then of course this symbol tells us that number is a negative number. These would still be considered whole numbers because they have no what? They have no fractional component. Numbering system. A writing system for expressing numbers that, a mathematical notation for representing numbers of a given set, using digits or other symbols in a constant manner, consistent manner. And these are symbols, so we learn symbols, right? You understand that? And we know the symbols we use to represent the weights 0 through 9. So these are the number systems that PLCs use. Of course, the PLC or the CPU inside the PLC does not understand decimal, but it allows us to use decimal. And then when we enter our high-level language program and we compile it over, then that would convert it over to binary for the machine, right? You understand that? So when I come up here and hit the A key on my keyboard, the computer does not see the letter A. It sees a code that represents the letter A, right? You know, we already looked at ASCII a little bit in this class, right? So these are the number systems we have to learn to deal with computers on the computer level. And even on our system, it actually shows us numbers, and the more you know, the more capabilities you have as far as fixing and repairing and programming these equipment that use these other things. So decimal, this is a base what? Base 10. Binary is a base 2. Octal is a base 8. And hexadecimal is base 16. Huh? That's an 8, yeah. And most of them tell you basically by their name, their base, right? So fixed point numbers. These numbers that have a fixed decimal and the digits move around the radius point. Numbers where fractional portions of the number is fixed. For example, money. Are you okay there?
Base 8.
Uh-huh. What's that?
You have a number that base 8.
Yeah. The numbers, what we do is we start with the numbers that's available. We use the symbols that we use for the decimal number system. So base 8, we would have a 0, 1, 2, 3, 4, 5, 6, and 7. And we have no more, so there's no such thing as an 8 in base 8. So if I was to come down here, write down 6, 3, 5, 4, but this whole, in base 8, that don't hold the weight of 10 to the 0, it holds the weight of 8 to the 0. This would hold the weight of what? 8 to the first, this would hold the weight of 8 to the second, this would hold the weight of 8 to the third. In binary, we've only got 2 digits, 0 and 1. 0 and 1. And so all we're going to see in binary numbers is we're going to have that. Now this gets us into problems because in your brain you want to see that as a decimal number, right? You understand? But it's not, because this holds the weight of what? 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. And that's the problem we get, is that our brain is so used to our brain is so used to decimal. When I see those combination of digits, I want to say that's 1,000. But in binary, this right here is an 8. It's the equivalent of a decimal 8. And that's going to get you in trouble. In hexadecimal, this is equivalent to like 32,000. So you got to be real careful. So that's why anytime I write a number, I'll come up here and do what? Yeah, I'll write the bases in. So if I come up here and put 2, then in your brain you got to say that is not 1,000. That'd be 8. If I converted that number to decimal, that would be an 8. And that's the problem. The less combinations you have, the bigger the more number of digits you're going to have to use to represent the number. So base 10, we have 10 combinations. Each digit can have 10 combinations. But in binary, each digit can only have what? 2. So it's going to take more digits to represent numbers. Floating point numbers. Now this is what the PLC calls real numbers and also floating point numbers. or exponent numbers. So floating point numbers can have a whole number, and it can be a real number, or it can use exponents. It all depends on how big your answer is. So this is a combination of two, but floating point numbers. So money, my Windows calculator doesn't do that, but most calculators give you the ability to set a fixed number of decimal points. And it's usually got FIX on your calculator. And then if you got a fixed number of decimal points and you start typing in numbers, and what it does, so let's say we have 2 decimal points. Well, when I start typing in numbers, the first number would go right there. And then when I type another one, this would come over there and this would move over here. And then when I type another one, it would keep shift, and what doesn't move? The decimal point. So used to in the old days when we had, instead of scanning prices, but money is always represented with how many decimal points? 2, right? Always in 2. Well, I'm not going to say it always. Computers might calculate it out to 15 decimal points, but they can't give you 0.00001, right? You understand? So eventually, when they pay you out, they're going to always pay you with at least 2 decimal points.
You don't have gas prices, they have like $2.30, they have a little fraction on the side. Why do you do this?
Well, they make you think that you're getting a deal. So they'll have 9/10s, right?
Yeah.
And people will say, well, Walmart's got it for $2.26, and they just ignore the what? 9/10s. So technically, it's not $2.26. Yeah, but everybody will do that. You know, how many people do you say where people throw in that 9/10s? So they always throw in that 9/10s, but to make it look like the gas is a penny less than what it actually is. But when they do it, it's fixed points. So when you start pumping gas, it starts filling in the first 2 digits, right? And then it moves over, and everything does what? Everything shifts, but the decimal point is what? It's fixed, right?
But all gas stations do it. So
Yeah, I know.
when you look at the number, it's really compared.
I guarantee you they get their 9/10s. But their display don't display the 9/10s, does it? So what's it do? It's always rounded up. 2 decimal points. Well, money is a perfect example of what we call a fixed point number. So the number of decimal points are fixed, right? And you can set your calculator up. I'll do this when I'm calculating grades. I fix it depending on what I round to. So if you look at Blackboard, your grade is rounded to 2 decimal points. In the Excel, you can set it up for the number of decimal points. So if you ever played around with Excel, you can set it up to be fixed. I got it somewhere. So if you use this side right here, these little things right here, that's what you're doing. You're setting up a fixed decimal number, right? Okay. So if I put it right there and start clicking this, and it starts adding digits, right? If I come up now, every number I enter here, right, will be what? Yeah, so I might come over and put something in there, but that's we set a fixed decimal point. And we do this a lot of times in Excel because it'll calculate a lot of digits, but we're only considered to round into so many digits. And a floating point number, this is where basically the decimal point can be anywhere in the number. On PLCs, this is also going to be where it'll shift into scientific notation. So this is basically what your calculator does. It does floating point numbers. So what happens is you start typing and you can put as many decimal points as you want to, but sooner or later your calculator is going to automatically shift into what? Into scientific notation, because it can only represent so many digits. So the two types of numbers that we can represent with, let me do this. So the two types of numbers we can represent is, if we use N7, it's going to say we use what type of number? Integer number. If we use F8, that's the two numbers that we have available.
6.3.
Yeah, that's the two numbers. That's the two numbers we can enter when we start dealing with numbers. So floating point would be numbers that have a fraction or numbers that need to use exponents. And then for integer numbers. And these are going to be limited, guys. So big numbers will use floating point numbers, and integers will use, and small numbers will use the integer without fractions. So that's the only two numbers. This is the only two types of numbers we have available. That makes sense? Okay. So decimal numbers, we can write a number. And how would I represent this in positional notation? So this would be 10 to the 0. This would be 10 to the first, 10 to the second, 10 to the third. This would be what? 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. So positional notation, I would say 1 times 10 to the third plus 7 times 10 to the second plus 6 times 10 to the first plus 3 times 10 to the 0 plus 9 times 10 to the minus 1 plus 2 times 10 to the minus 2 plus 8 times 10 to the minus, I left off my minus 3. And that would be the number of positional notation. Then I would take my powers of 10s and convert them over to the actual decimal equivalent of those powers. And then we'd add them together. We're okay. Everybody okay so far? People still writing?
Oh, that's how far you call that the positional notation.
This is called positional notation right here. So positional notation means, positional notation just says we're writing the number out longhand and showing you exactly what each digit holds for the overall weight of the number. So when we say 6, what's the weight of 6? Well, it depends on where it's at in the number, right? You understand? So if I put a 6 here and a 6 there would not be the same. Even though the symbol is the same, it would not be the same because it's in a different position inside the number. Right? You understand? So on the integer portion, the further we move to the right, the more weight that digit has over the total whole value of the weight of the number. And the fractional portion is different. So the fractional portion, the more you move, did I say right? So on the whole number, the more we move to the left, the more weight that digit has to the overall weight of the number. On the fractional number, the more we move to the right, the less weight it has to the overall weight of the number. So if I was working and they gypped me of one digit right there on my pay, I would be upset. If they gypped me of one digit right there, I would go up and complain, right? You understand? But way up here, so the more you move to the right, and over here, of course we don't see this, but even down in here, if they gyp me 1 penny, I'm not too upset, right? You understand? The processor in a computer only understands the numbers and codes represented using ones and zeros, because it's very easy. Now you have to understand in a computer, there's not even anything as ones and zeros. It's either we put a voltage there or we take the voltage away. Right? Does that make sense? So, but now we can represent binary very easily with electrical. You know, we could say, okay, 5 volts represents a 1 and 0 volts represents a 0. So that's the way we represent binary. And if we're going to represent binary in electricity, we've only got 2 choices. We can either represent it in current or we can represent it in voltage. By far, voltage is the most popular way. All images displayed on a computer are a series of dots. If you got up here real close, you can see these little kind of squares up here. So they're not technically round dots anymore. They're originally on the old cathode ray tubes, the dots were actually round. But most of the time on our displays now, they're actually little sticks. And I forgot to bring my microscope over, guys, even though I went over there, but I'll try to do that. So y'all can come up here and look at my computer screen with a microscope. It's just a bunch of little sticks, red, green, and blue, and then on a black background. That's all these things are. So all we're doing is either turning one on or doing one, turning one off. And the computer just displays patterns. They have the ability to process information. So they can take that binary number and display it as a decimal number very, very easily. Very easy. Computer programs can process binary codes in a series of dots. A computer can use to display images on screen. This means the computer can display binary numbers, decimal numbers, hexadecimal. They can display any base because the computer's decided it knows the dot patterns to put up there for different things. So our computer uses different bases. If you ever got into what we call the registry, got really into the computer and got into what we call the registry. If you don't know how to get into that, guys, y'all need to stay away from that. But it displays a lot of binary information for us. It displays a lot of hexadecimal information. If you got Windows, I don't use this when we take tests because that's cheating. But this Windows calculator, you can switch it over to a programmer's calculator, and it gives you all 3 of those bases.
Is that on mine? No.
Yeah, if you got Windows, it's on yours.
No.
Well, if it's got a calculator, it would surprise me that they don't do this. So I can come up here and I can enter a number, and I've got 1, 2, 3, 4, 5, 6 digits. Look at that same number in binary. Because we only got how many combinations? 2. Yeah, look at the same number in octal. It's still a little bigger. Look at the same number in hexadecimal. So hexadecimal has better resolution because it's got more combinations. So the number actually looks smaller. But there they are. And look at that. It's got E in there. Huh? No, that's not an arrow. That's an E. So we'll get into hex in a minute. So hex, we ran out of combinations used in the decimal numbering system. So we go 0 to 9, and then it goes A, B, C, D, E. So E is actually equal to a 14. Close. So a computer can display, it can take a binary code and display anything on the screen because it processes information, right? So basically what we see is the decimal number system. And why? Because that's the only number system we understand. But it does do some hexadecimal and it does do binary if you can get into it. So here's our basis. So this explains hexadecimal right here. So decimal, there's our 10 combinations, which we're very, very familiar with, right? Binary, we only have 2 combinations. What are they? 0 and 1. Octal, we've only got 8 combinations. That's 0 to what? 7. Then hexadecimal, we need to get 16 combinations with a single digit. So what did they start doing? Yeah, they started using letters. So this would represent a 10 in base 10. This would represent, A would represent a 10 in base 10. B would represent an 11 in base 10. C would be a 12, right? Right. D would be a 13. E would be a 14, and F would be a 15. And that's all the combinations, 0 to 15. Well, here's the 4 bases. And we do this. I mean, I can show you an example right now. Oops. 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 I got my, let's see what comes up. No, I don't do that. I was one letter down. So accessories, system tools. We're looking for system information. So this is the addressing map for the computer. It shows where addresses. And you see when you get down here, what it say? So the programmer interrupt controller is that. So what base are they using? This is base 16, right? Here's the memory map for the computer. This guy's got a bunch of memory in it. So you can see right off the bat that what base is it using. As soon as you see L's and A's and D's and that kind of stuff, you know it's what base. Now that's a big number. If we converted that to decimal, that would be a big number. Let's see if we can do that. So I got it in hex. Let's put this number in right there. So that would be what? So notice my keyboard changes. Now over here I got what? Yeah, letters, yeah. So that would be F, let me do this, my F, E, D, and then 4 F's, right? And we'll convert this over to decimal. That's the actual decimal number that represents. This would be the binary number. Now, if I told y'all to write that down, if I told you to write that down, which one would you be able to write down easiest? X. That, or that. Or even octal. Octal would be easier to do too. This is the advantage of binary used by computers and digital devices to electrically transmit, store, and process information. Easily to electrically transmit and receive accurately. Easy to electrically store for later use. Each of the to electronically perform math and logic. Disadvantage, it requires a lot of digits to represent decimal. It requires a lot of circuitry, but the circuits are a lot less complicated. We okay? So that's supposed to be easy, not each right there, guys. Octal, used by computers to represent large binary numbers with what? Here it is. Was the first high-level numbering system used by computers and PLCs to represent binary numbers and code. These are still, this is still available on PLCs. We don't use them very often because of the resolution of hexadecimal. That's the primary number system we use now to represent large binary numbers. And of course, the biggest problem we have is we want to see numbers in what base? Decimal. That's what we see. That's what we see. Hexadecimal used to represent large binary numbers and codes with fewer digits than decimal and octal. After decimal, the most widely used number system used by computers and PLCs to represent binary numbers and codes. The disadvantage is what? Hard for us to understand. Hex really gives us a problem. We see numbers as decimal until we see like a or B in there, and then we say, oh, this is not decimal. What time is it? What did I tell y'all to do every hour?
10 minutes every hour.
Everybody did that. Let's take a break. If you came in late, you need to let me know. So binary, this is the only numbering system that a computer understands. And of course, a programmable logic controller is a computer. So all it understands is binary. In this class, we're not going to use binary a lot. If you take the advanced PLCs, we will use it more because we're getting into the more advanced features of the PLC. The primary numbering system we'll use is this semester is decimal. But we'll need to understand what's going on when we get into integer numbers and figure out why the PLC has a certain range, because it uses a certain number of bits to represent those numbers. And so that's going to specify bits. Uses a certain number of digits to specify those things. So this would be a binary number. And of course, I put a little 2 down there because this would be legal in all bases. This would be a legal combination in in binary, hexadecimal, octal, but it'd have a different weight. This guy here holds a weight of what? 2 to the 0. To the first, to the second, to the third, to the fourth, to the fifth, to the sixth. Everybody okay? In fact, I'm going to drop off that digit. I don't need that digit because it has no weight, right? This would be what? 2 to the minus 1, 2 to the negative 2, 2 to the negative 3. Okay. So if I wrote this down in position notation, it's going to take a lot of space. This is going to be 1 times 2 to the 6th plus 0. Why do I even need that? Because if I take 0 times any number, it's 0. So let's just drop all the zeros out of this. So I'm going to jump down to the next one. 1 times 2 to the 4th. Y'all understand why I did that? Okay. Plus 1 times 2 to the 3rd. Plus 1 times 2 to the 1st. Plus 1 times 2 to the minus 1. Plus 1 times 2 minus 3. Well, why do I even need the ones? I mean, because 1 times the number is what? Itself. Yeah, so I could say 2 to the 6th plus 2 to the 4th plus 2 to the 3rd. So don't let me plus 2 to the... what did I do? Oh, 2 to the 1st, right? Plus 2 to the minus 1 plus 2 to the minus 3.
So we don't need that.
This? Hey, well, we're not even gonna use that. This is just showing you using positional notation and where all this came from. Now, to get this to decimal, all I need to know is what 2 to the 6 is equal to in decimal. Right? You understand that? So we could use our calculator. You could use a little chart. I gave you all that chart, which got powers of 2's on there. So I could say, okay, this would be 64 plus 2 to the 4th. What's that? 16 plus 2 to the 3rd, which is 8, plus 2 to the 1st, which is 2, plus 2 to the minus 1, which is what? No, it's the reciprocal. It's going to be 0.5 plus 2 to the 3rd. So that's going to be the reciprocal of 8, which would be 0.125. Then I could add these together. So when we add them together, what do I come up and get? Huh? It takes a calculator to do this, guys. Yeah, that's a lot. What's that? 82. And we've just converted a number from binary over to decimal. No, I'm sorry. Yeah, this is the base 10. So what I'm doing is I'm indicating the base so we don't get confused. That 0.8, these digits, these symbols, 82.625 would be legal in 2 different bases. And I don't want you, what's that? I'm just writing down what y'all say, right? That way I don't get credit for making the mistake. 90? So then, notice I put that little thing down there to let you know that this was what base up there? Base 2. So on this side, you just use whatever you use over here. So on the minus, so on the minus side, this would be equal to 1. What's 2 raised? This would be 1 over 2, right? Everybody understand that? And 2 to the 3rd, which would be 8, so that would be 1 over 8. So if I was going to do this, are we ready? I'm going to erase this. Everybody okay? Okay, are we ready? So this, huh? I'm listening. Because it's 2 to the minus 1st, which, but, and this is the way you do it, guys. I'm gonna erase this right now, and we'll just make up a number, a binary number. And instead of using powers of 2's, I'm gonna write the decimal equivalent of the powers of 2's. So what I'm gonna do is I'm just gonna make up a number. Well, over here I'm gonna just go 1. Then I'm gonna double that. That goes to what? 2. Then I'm gonna double that. That'll go to what? 4, 8, 16, 32, 64, 128, 256. And what I've just done, that's all you got to do. You don't have to know 2 to the 1st, 2 to the 2nd, 2 to the 3rd. You start with your least significant whole number. You go 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, 16,000. Right? Y'all understand? I've dealt with binary a what? A long time.
That's not a computer requirement.
So I know those, right? You understand? I just know them. Over here, this would be, I just started over here. I skip over the one. There's only one. This would be 1/2. This would be 1/4. This would be 1/8. What would the next one be? 1/16.
132, 164, 128.
So you just repeat, you skip over 0 because 1 over 1, the reciprocal of 1 is 1, right? And then you would just go over here, 1/8, 1/16, right? And you just come over here and do the same number. Guys, I've been dealing with binary a long time, right? You'll see that. So I know powers of 2s all the way up to 65,536. And then I start having problems. No, I never get that far. But you got a calculator. What I've got is you've got a chart. I gave you that chart, right? You understand? And I carry powers of 2s all the way up to what? 2 to the, on your powers chart. 2 to the 40th, which is I don't know that one, guys. A long number. But you could do it on your calculator, 2 raised to the 45. So what I would do is I would just come up here now, if I wanted to know this decimal equivalent of this number, instead of using powers of 2s, you know, this does not hold a weight of 64. It holds a weight of 2 to the 7th, right? You understand that? But the problem, 2 to the 8th, but 2 to the 7th. Yeah. But what we're doing is we're going ahead and converting it. We're skipping some steps and just writing the decimal equivalent of that. So what would this number be? It would be 64 plus, I'm going to leave off the 32. Why am I going to leave off the 32? Because it's a 0, right? I'm going to write down the 16. I'm going to write down the 8. I'm going to write down the 2, right? And let me keep going. And then I'd write down the what? 0.5. And then I write down 0.25. And then I write down 0.125. And I would come up here and I'd add those together, and that would be my decimal number.
That's a quick way right there. Yeah.
That's a real quick way. And now you got the decimal equivalent of this number. Now it makes sense. This number over here makes no sense to you. It makes sense to me because why? Well, I've been doing it for a long time. I mean, I came up through microprocessors, programming in machine language, 1s and 0s, programming in actual machine language. And so binary was a number system that we really, really had to learn. Like I said, in this class, we're not going to deal with it much until we get into integers and floating point numbers and stuff like that, when we actually get into some of the things that we'll deal with. But when you get into if you're signed up or you're going to take the advanced PLC class, then we're going to delve back into this a lot more, because we have the ability to do logic on large numbers. Now, you have a lab that you're going to do, and you're going to convert these over. I don't forget which lab it is. You know. Everybody got their lab book? I don't know. It's numbered systems. Which lab is that? Lab. I don't suppose it is. No. A lot of numbers, right? Okay, hold on. Let's get through this. We're not gonna do the lab right now. We might let y'all start on it just to see if y'all got any problems toward the end of the class. Yeah. Yeah, this is a take-home lab. There's some labs that are take-home lab that we'll do it at home.
And you're to be due on Monday.
Yeah. And that way we'll come in and we can go over it to make sure we don't have any problems right before the test.
What lab number you talking about?
I think lab 3. I think they said 3. 3? Lab 3? Same as the book? Yes. Page 5.
It's gonna help with our about this.
Yeah. No, definitely a lot of it.
Number system.
Frying your brain. Is that what you said?
No, I said, this don't look bad. I'm like, after giving them.
So, this is the next slide that I have. So all we do, this is whole numbers, and we're going to deal primarily with whole numbers in this class, but in your lab you'll need to, I think in that lab you do have some fractions in there. But we'll show you in a minute how to go the other way. And you will not be able to use your calculator on the test.
Huh?
You will not be able to use our calculator on the test, and there's really no need to, because why? Because this math is not beyond the scope of. I'm a firm believer that if you can't do the math longhand, you don't need to do what? You know, because you still don't understand it. So if you can't do it longhand, you're going to take for granted whatever that calculator gives you. And you don't realize if it's gave you the what? The wrong answer. That's probably wrong. You just type something in wrong and you get it equal. So all we do is what? On whole numbers, we just start with what up here? 2 to the 0, but any number raised to the 0 power is 1. So no matter what base we're going to deal with, that first one's going to go be 1. So in base 10, it would be 1, 10, 100, 1,000. And then what do? We add the decimal equivalent weights of only the digits that have 1s in them. We don't even use the zeros, because what's 0? So this is what we did. We said this would be 0 times 128. Well, what's 0 times any number? 0 times any number is 0, right? Any number raised to a power is 1. Yeah, you thought I was talking about power.
Right.
So all you do is just add the numbers that has what in?
1.
So down here, what are they adding? They're adding 256. Why did we choose 256? Because it's got a 1. Then what? 32, 16, 8, 2, and 8. Add them together.
What base is this base?
This is base 10. This is base 2. Yeah, this is base 2. The top number is base 2. The bottom number is base 10. It's the base 10 answer. Those two numbers are equal to each other. This would be legal. To us, we wouldn't see that, because we'd see that as a big number. We'd see this as a small number, right? But look how many binary bits it took to represent 314. It takes a lot, because the base 2 numbers only got 2 combinations, right? And base 10 has 10 combinations per digit. Are we okay? Glad you think of some people, and this is what we're talking about as a class, because some people do what? They catch on real fast. Some people take a little while, and guys, y'all need to take care of each other. Y'all need to come in and y'all need to set up a time. And like I said, I'll leave the room open. Even when we start going to lab, when I leave, I'll leave that. I can let y'all stay in the lab and work if you want to. But you can work as a team, but don't cheat, right? Because if you cheat, you're not learning anything. I can more understand people cheating, and I don't like cheating, but in like English, but I can't understand people cheating in their trade. I just can't understand that. I can't understand why somebody would cheat in their trade. Then they get out of there and they don't know what they're doing. And then they say, well, don't hire those people from Lawson, they don't know anything. It always surprises me what students will do to cheat. And it takes more thought to cheat than it does to learning that. It always amazes me. So everybody okay here? So here we're going to deal with primarily whole numbers, but everybody okay on the fraction? Right? Okay.
You call them the binary fraction.
No, a binary is a numbering system that can't have a fraction. There's no fractions in this number. How do I know there's no fractions in this number, Gary?
Well, you know,
There's no decimal point. There's no, here we call that, yeah, this don't have a this number is a whole number. It has no fractional component. There's no radix point in that number at all. Huh?
well, I guess.
Yeah, we just went over some of it. So everybody okay here? Now, how does the book teach y'all to go from decimal to binary?
Go on chart.
No, that's not the way they teach it.
We didn't have this in 40.
No, we didn't. We didn't. When the original Star Trek came out with Captain Kirk, they had a group of aliens that came aboard. They was called binoids. They spoke in the binary language. So they clicked. Huh? It's telling you to divide. Yes. Okay, so this is the way the book teaches it, guys. I'm not going to teach it that way. Well, let me show you the way the book shows you to do it. And you can use this method if you want to, but we'll show you an easier way. So we had 314, right? So if I was going to go to base 2, the first thing they tell us to do is divide it by the base. And this will work for any base, guys. What's 213 divided by 313 divided by 2? What's 314? What did I say? What's 314 divided by 2? What's that? And what remainder do we have? We have a remainder of 0, right? So here I'm going to put R. So then what I do is I bring down the 157 and I divide that by 2. That gives us what? 78 with a remainder of 1. 0.5 is 1, right? So how do you figure out what we got to have the whole number remainder. This is back when you're in elementary school when you didn't use fractions. So how do you find the whole number remainder? You multiply it by the base. So if you had 0.5, you multiply it by 2, that's going to give you 1, and that would give you the whole number remainder. So every time you hit 0.5 on your calculator, I will put a 1 out there. Every time you get a whole number, I'll put a 0 out there. Okay, then I'm going to bring this number, 78, I'm going to divide that by 2. What does that give us? What's that?
Okay, well, 38.
You say everything for the whole number is 0, right?
Well, you know, every time I do if you're doing it with a calculator, every time I divide by 2 and get a 0.5, I'm going to write a 1 over there as my whole number remainder. If it comes up to be even, if it doesn't have a fraction, I'm going to write down a 0 over here. So what's 78 divided by 2? 39. Is there a 0.5 out there? Okay, so I'm going to come over here, and I'm over here in my remainder column, I'm going to write down a 0. Now, most of you are using a calculator to do this, right? I'm going to show y'all, we don't. Then I'm going to take 39, and I know this is going to give me a 0.5 because it's an odd number, right? I'm going to divide this by 2, and what does that give me? What's that? 19, so I got a 0.5, so I'm going to write a 1 down. Then I'm going to say 19 divided by 2. That's going to be 9, and I'm going to write down a 1. Right, then I'm going to bring my 9 down. I'm going to divide this by 2. What's that? 4 with a remainder of 1. Hopefully I don't run out of space. Then I'm going to take 4. I'm going to divide that by 2. That's going to give me 2 with a remainder of 0. And I'm going to take 2. I'm going to divide that by 2. That gives me what? 1 with a remainder of 0. Huh? And then I'm going to take 1 and I'm going to divide that by 2. That's going to give me what? That's gonna give me 0 with a remainder. Then what I'm gonna do is I'm gonna make this number fall in this direction. So this is my most significant digit, and it will always be a 1. You'll always end up with a 1 in there. Okay. Then I would come over here, I'd say 1, 0, 0, 1, 1, 1, 0, 1, 0. This is base 2, and this should be the same thing that we had right there. It is, right? Did y'all enjoy that?
So you went from the bottom up.
Yeah, so what's at the bottom, so what you do is you let the digits fall to the right-hand side. Did y'all enjoy that?
Go back to that other slide.
1, 0, 0, 1, 1, so 1, 0, 0, 1, 1, 1, 0, 1, 0. 1, 0, 0, 1, what?
Whoa.
You try to write that down though.
Okay, you skip the first one, 0. Stop. 314 is right.
1, 0, 0, 1, 1, 1, 0, 1, 0. 1, 0, 0, 1, 1, 0, 1, 0, same number.
So you just skip the first 0.
What do you mean skip the first 0?
314 divided by 2.
Yeah, no, that's the 0 here. So here's that 0 right there. Here's this 0, here's that 1 right there. There's that 0 right there. You let it fall to the right.
I'll start on the other end.
Yeah, no, you let it fall to the right.
Well, I had to know.
Now this is the way the book teaches. And what does this equal? Okay, 314. Even number, right? Y'all understand that? Okay, let me show you the method that I usually use. Are we ready? What I'm going to do is I'm going to take my number. What's my number? Okay, I'm going to take 314. And I'm going to start writing down just a chart with powers of 2s in it. 314. I'm going to start with 1, 2, 4, 8, 16, 32, 64, 128, 256. And I usually like to go one pass to make sure I got enough digits up there. How's that hard? 1, 2, 4, 8, 6, right? Okay. Then what I'm going to do is I'm going to look and see. So what I've done is set up a chart that's got the decimal equivalent of my powers of 2. What I'm going to do is figure out what's the largest thing I can subtract from 314. I can't subtract 512 from 314. Okay, so what I'm going to do is I'm going to put a 1 out here. I'm going to write down 314 and I'm going to subtract 256. Can y'all subtract that without a calculator? Okay, so what do y'all got? What's that?
No.
58.
Hold up.
Yeah, 44 plus 14. 58. It's 60. 58.
So y'all agree?
It's 60.
It's 58.
Right.
58. 44 plus 14. 58.
Right.
Are we okay? Are we in agreement here? Okay. What's the next thing what's the next highest power I can subtract from that? 32. I'm going to put a 1 over 30 under 32. Write it down and subtract this. So y'all agree on this?
Okay, that's 26.
Okay, 26. What's the next highest thing I can subtract? 16. This is going to be 10. What's the next thing I can subtract? 8. That gives me a 2. What's the next thing I can subtract? 2. I can subtract a 2, right? Okay. And so I've subtracted 2, and that leaves me what? 0. Then I'm going to come in and fill in the zeros of the things I did subtract. And that's it. 1, 0, 0, 1, 1, 1, 0, 1, 0. So all we got, and by, guys, I can count in powers of twos. I've done it so long, right? But what you're gonna have on the test is you're gonna have that chart right there. And that chart right here, because we understand that this is something new to you, right? And that chart goes all the way up to 10 to the 2 to the 40. So there shouldn't be any numbers we should deal with, right? You want to do another one? Huh? We ready? We ready?
I had to grasp it.
Huh?
I had to grasp that.
Subtracting?
Oh, I did. If you get the first is 58,
No, the first subtraction. So what I do
you subtract it.
What I do is I find, and this, y'all know what the problem people have right here is they try to subtract this from that. And we're not going that way. So what we do is we subtract the highest power of 2 from the number we're trying to convert over to power 2. And somebody in this class is going to do that. They're going to try to subtract this from that. So what they'll do is they'll say 314 and they'll subtract that from 512 instead of doing it the opposite way. And I don't know what to do about that. But this size of this class, somebody's going to do that. So what I do is I find the highest power. This is the number I'm going from, 314. And I'm going to binary. So what I do is I lay out my chart, right? You understand? And like I said, I like to go, and by George, by the time you get down to here, you better not have any digits left over. Because if you did, it means you didn't do it right. So you should either subtract and get a 0 before you get here, or you should get here. If it's an odd number, you will always have a 1. When I add an odd number plus an odd number, there's only one way we can get an odd number, right? You understand? And if we add an odd number plus an even number. Well, all these other numbers are even. So the only way I can have an odd number is if this digit right here is set. So if this digit right here has got a 0 and if that number is even. If this has a 1 in it, then the number is odd. So that's another kicker. If you start off with an odd number in decimal, you better end up with an odd number in binary, right? You understand? And you can tell right off the bat. It's real easy in binary to tell if it's an odd or an even number. What do you look at? You look at this digit right here. If it's a 0, then it's going to represent an even decimal number. If it's a 1, it's going to represent an odd decimal. So if you got an even decimal number, you're going to subtract down to 0 before you get here. If you got an odd decimal number, you're going to come all the way to here, right? You understand that? Yes or no? But eventually, you're going to subtract and get a 0. You're going to subtract and get a 0 answer. So if you keep subtracting and you get all the way down to here and you still got some subtracting to do, what does that tell you?
You did it wrong.
You did it wrong. You didn't go high enough in your power to do.
One question.
So here's 256, Gary. This is the number I'm going from. I find the biggest power of 2 I can subtract. So I wrote down the 256, and what did I write down in my binary number? How many times can you subtract it? 1 time. And then I came up with what? 256. Can I subtract a 128 from 256? No, from 58. Can I subtract a 64? What can I subtract? A 32. Okay, so I write down the 32 and I subtract them. 1 time. If it subtracts more than once, you know what, right? You done what? You done something wrong. So let's let y'all do one. Y'all ready? So let's do a little bigger number. Let's go to like 897. So this is an odd number. So you're going to end up subtracting out, and this is base 10. So you're going to have to go all the way down to bit 0 to the last to 2 to the 0, right? What's the first thing I'm going to do? Do me a chart. But we're not subtracting 896 from 1,024. We're not even gonna use 1,024. What I usually do is I go one bit position past that, so make sure I have enough numbers. That's all I do. And I won't never subtract. So what are we gonna do? We're gonna subtract these from what? From that, right? So we're gonna subtract the equivalent, power of 2, the decimal equivalent of the power of 2 from the decimal number we're converting over to. So. And you look at your lab, some of these numbers get pretty big. You got it?
Yep.
We got it? Okay, so where do I start at? We usually, when we read numbers, we read them from the most significant digit over to the left, right? So where do I start at? 512? Okay, so what? Somebody called it out for me.
1, 1, 0 all the way. Then, 0, 0, then 1.
That good? So anybody use the divide by 2 method? Or do you do the subtract method? Yeah. The book don't teach this though.
Why did it make it hard?
I think it's in my head here. Everybody get 129 after 256.
Yeah.
So that, subtract 128 from it, you get 1.
Yeah, and then you can't,
All those.
you can't subtract a 64, you can't subtract a 32, you
all
can't
those
subtract a
become
60,
zeros.
that becomes 0.
Become 1.
Anything you don't subtract comes up in is a 0, right?
So if
And-
I take a 1 and I subtract a 1, I get a 0.
Yeah, that's what we're shooting for. We're not writing down what we do in the division. We're writing down, if we can subtract from it, Gary, we're gonna write down a 1. If we can't subtract it, we're gonna write down a 0.
You can subtract a 1 from the 1.
That's right, so you write down a 1. Because you could subtract it, right? Everybody understand?
I got it.
Yeah. So we understand, so this has a chance of being right. So if you start off with an odd decimal number, you better expect an odd binary number, right? You understand that? So right off the bat, if you get an odd number, it don't mean it's right. But that's what I tell people, sometimes it's obvious that it's what? That it's wrong. If you start off with an odd decimal number, you better end up with an odd binary number. And what determines if a binary number is odd?
The number at the end.
This bit right here, bit 2 to the 0. If this is a 0, then that number is an even binary number. If it's a 1, then it's an odd binary. And an odd binary number had better convert over to an odd decimal number. And an odd decimal number. An odd number is odd in every base. So an odd decimal number would be odd if we converted it to octal. It would be odd if we converted it to binary, right? You understand that? And it's real. And we're not saying if you start off with an odd and you end up with an odd, it don't mean it's right, but at least it has a chance of being right, right? You understand what I'm saying? In my mind, that's just the number we made up. What do you mean the last number?
That 7 is supposed to be the odd number.
Well, you learned that hopefully you learned in decimal how to identify odd and even numbers. Now decimal is a little harder because we have 1. So if it ends with a 1, it's odd, right? If it ends with a 3, it's odd. If it's at 5, it's odd. So in decimal, you had to learn what odd and even numbers is. Like 2, 4, those are evens, right? 1, 3, 5, 9, 7 is what we consider to be an odd number, right? So an odd number means, right, If we divide it by an even number, we'll always get a fraction, anyway. But in binary, it's a little easier because you're not trying to learn the even combination. In binary, you're just looking at one little bit back there, right? The 2 to the 0 bit. That's the one that's going to determine if the number is even or odd. And all I'm saying is if you start off with an odd decimal number, you better end up with an odd binary number. So if you start off with an odd decimal number and you end up with an even binary number, you know it's what? You know it's wrong. Or if you start off with an odd binary number and you convert it to decimal and you ended up with an even decimal number, you know the answer is wrong. Now, if it comes up to be odd and even, it don't mean it's right, but at least it has a what? It has a chance of being right. And this is what bothers me sometimes when students come up with a number when it's totally obvious it's what? It's wrong. So if you come up with a hexadecimal number that appears to be bigger than the binary number, it's got to be wrong because that hexadecimal number has a better resolution. Okay, guys, y'all take a break. 10 minutes. That's no surprise, Gary. It's you.
So we did that with the power of 2. If you wanted to, you can use this chart with the 16 going up.
No, not for a binary.
You can't do it with binary. So binary, you have
If I was to come up here, well, odds are, hopefully you don't know that. So first thing we do is what? Draw the chart, right? With the decimal equivalent of the powers of 2. Then we subtract the what? The largest possible decimal equivalent of the powers of 2 from that, and we put a what under there. A 1, right? Okay. Then repeat steps until the answer to each subtraction until you come up and get what? 0. If it's an even number, you're gonna subtract out from 0 before you get to the 0, right? You understand? If it's an odd number, it's gonna come all the way over. Place a 0 in all remaining bit positions to the right. So here we're doing 1058 decimals. And what's the biggest thing we can subtract? Yeah, 1024. And then we got 634. So what's the next thing we can subtract? 512, right? And then what's the next thing we can subtract? 64, right? Okay. Then 32, right? 16, right? 8, 2. Then we're through. Then we just fill everything in with what? 0. We've just gone from a decimal number over to a binary. Well, let's do that. So I'd come up here and I'm going to add, so we're not going to go back. We're going to convert this over. So to convert it to decimal, all I have to do is write down the decimal equivalent of each, only the digits that's got 1 in it. So I'd write down 1024. I'd write down 512. I'd write down 64. I'd write down 32, 16, and 10. I can do 8 2 in my head, right? Add this up, and that'll give us our decimal number. I know I better expect something greater than 1024. This bothers me too. If they'll have a 1 in 1024, and their decimal number comes up to be less than 1024, you know it's got to be what? Wrong. It's got to be greater than this first. Your answer's got to be greater than that. It's got to be greater than 1024. Looks like it's going to be a lot greater because we got a lot of 1s in there. So what do we come up and get?
It's like a matrix.
Are you talking about the movie? So what do we get when we add it? Double check our work. What's that? base 10. And that's what we started out with. Well, that's always good. And that's one way you can double check your work, right? You can come back and convert it back. If you come up with some numbers, it means you got the right answer. Okay, decimal to binary, we've already looked at that, right? Okay. Convert the integer parts of the number. We're not going to do that. I needed to get rid of this slide. Y'all like that? Which one do y'all prefer? So if that's still up there. Now think about this. So what I've got here. I should have just clicked on the right slide. So here's 10 combinations using lights. So that'd be a 0, this might be a 1, this might be a 2, this might be a 3, this might be a 4, 5, 6, 7, 8, 9, 10. What digit is that? Maybe a 0. Okay, so y'all just guessing at that, right? So this is the problem we have trying to transmit decimal numbers. It's so hard to translate what I'm actually trying to get you. Okay, there's 4. So that in binary, that would be a 0, that would be a 1, that would be a 2, that would be a 3, that would be a 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So something happened. So what would happen if I came over here and just drew these two in? So this would be 1, 2, 4, 8, right? Everybody understand where I got that, right? Yes or no? Okay. So what if I came over here and this one right here was colored in and this one right here was colored in? What am I trying to send you? I'm trying to send you 5. 4 plus 1, right? You understand? So what I like to use like a flashlight. So here I'm trying to send you I'm trying to send you numbers with flashlights, and I have 10 combinations, 0 through 9. And I'm over there, and I turn on my flashlight, and I select the numbered line. The light would be a certain brightness. How many of you could decipher what I'm trying to send you? Probably nobody. So everybody here came up with a little different answers, right? If I got over there, how far away could I get with some flashlights and turn them on or turn them off? How far could you see those lights on or off? No, not even a laser, just a regular flashlight. How far off can you see a flashlight pointing at you?
It depends based on
Huh?
your vision.
Okay, so let's say you have 20/20 vision. And there's no trees or anything between you, and it's not night. It's even during the day. Let's say the flashlight is this big. No, how far could you? But think about me trying to send you a decimal number with light. Tell me how far could you differentiate a binary number with light? Ships use it all the time. In fact, that's one of their most secure method of communication because they're not sending information over the waveforms. So one of the things they do in the military is they point those things. They got blinders on them, kind of like some of the red lights have, so you can't see where the light's green when you're coming in at an angle, right? You understand that? Y'all seen the lights with the blinders on them? And they point them at the other ship, and then they see dots and dashes. And they pick it up and they write it down. And how far can those ships be apart? Well, as long as they're not over the horizon, they can see those things and get their communication. So this is one problem we have. We're trying to use, so if I'm going to represent numbers and I'm going to do it electrically, we got 2 options for us. We can either use voltage or we can use current. Now what happens with voltage when we're trying to send voltage over distance through conductors? We lose. We call Alabama Power calls it line loss, because if you try to put voltage into a load, you're going to have current, everything has resistance, right? We don't understand that, but everything has resistance. If you put current, every conductor has resistance. And if you put current through resistance, you have a voltage drop. Y'all learned that in DC. So Alabama Power is constantly fighting that, what they call line loss. So it means you're over here and I'm trying to use 5 volts to represent a 1, right? You understand? And then I go way over here and I use it, now all of a sudden it's 3 volts and it's no longer a 1, right? I mean a digit. So what we do is instead of using voltage levels to represent each decimal digit, we either say, okay, if a voltage is there, it's going to be a binary 1. If the voltage is not there, it's going to be a binary 0. And now we can sacrifice some voltage. So on digital, TTL, by the way, digital is 5 volts, but they'll accept anything over 2 volts is what we consider a legal 1. So it means I would generate 1 volt over here, but if I get over 2 volts over there, it's still considered to be what? It's considered to be legal. So now all of a sudden we can, with 1s and 0s, voltage or no voltage, we can transmit data over extremely long distances without having very much loss. So binary. So when you get your information on your phone, odds are it's digital now, right? You understand? Because we can transmit it a long way and we can sacrifice a loss on that, right? You understand that? Doing math, we're going to show y'all some math. Math is the circuits that do math. If I was going to try to design a circuit that does math, we're analog math. So let's say 1 volt represents a 1, 2 volts represents a 2, 3 volts represents a 3, all the way up to 9 volts. And I'm trying to design a circuit that recognizes a 9. It's going to be very, very that can differentiate between a 9 and a 3, right? You understand? Very complicated circuit. But binary, it's either going to be what? It's going to be on or off. So what that means is the circuitry that processes, that does math with binary information would be very, very simple. I could draw the circuit. That would add a binary number. Then plus, doing math is easier for electronic circuits to do binary. It's a lot easier for us to transmit over a distance without having much loss, right? You understand? And then of course, the circuitry and doing logic is binary, guys. Y'all understand that? So this is why computers don't even attempt to use. When I first got in the military, the computers that processed the flight control systems on the airplanes I worked in was basically an analog system, and it was very, very, very complex, right? And the CPU in the plane was probably this wide and that big that processed just to make the plane fly straight. And now everything is what? Yeah, computers, and now they do what? Everything is dropping down. But what we have to understand is that it requires more circuitry to deal with binary, but the circuitry is not complex at all. So this little circuit right here, this would add binary numbers. And this would be the carry right here. And that's all there is, and that would add a binary bit right there. I wouldn't care about it. But the problem we have with binary is it gets so dang complex, right? You understand? So if I came over here and wrote down this binary number, all y'all would freak out. But if I was to take this binary number, and what I'm going to do is I'm going to just split it up in groups of 4s. Y'all don't let me mess up. And if I was to write this down like this, how many could get that right? Now, you might not understand it, but if I was going to give you this large binary number, which would you prefer? 1 0 1 1 0 1 1 1 0 1 0 1 1 0 1 1 1 1 0 1 0, or 2 D D 6 F 5. Now, one of them's base 2, one of them's base 16. I went between base 2 and base 16 without having a calculator, without having a chart. I did it what?
Magic.
Magic.
Is that right?
So what we're gonna,
Is that right? So,
we could convert them over.
So you said 5 and 16. 0, 1.
No, this, I'm doing this, guys. All I'm doing the subscript for is to let you know what base I'm dealing with. That 16 means nothing as far as the weight of the number. It just means that that bottom number is a base 16 number. The top number is a base 2 number. That's not really,
Oh, you talking about all of that.
that's base 16 number. Or if I had a base 16 number, like 2D59, I'm not going to do it. I'm not going to do it. Let's change this. So that would be the binary number that that base 16 number represents. This is base 16, this is base 2. So what I'm saying is that if the computer is going to display large binary numbers, odds are it's not going to give it to you in binary. But it's going to give it to you in a base that if you understand it, you can go between these bases without doing division, without doing subtraction, without doing all this garbage that the book's teaching. So the book teaches you how to go from decimal to hexadecimal by dividing by 16s. We don't ever do that. What we do is we use hexadecimal and octal to represent large binary numbers. That's what we use them for. We very seldom want to know what this number right here actually has the weight of. This is counting in binary. So this gets people confused too. You want to see that as a what? You want to see a 10. 1 0 is the base. It's always the base. So if I came up here and this right here in base, that right there in base 16 would equal to 16. This right here in base 2 would equal to 2. That right there in base 8 would be equal to 8. So that combination of symbols, 1 0, will always equal to the base. So this is the way we would count. And what you're doing is you're looking at this like this, right? This would be 1, and how many digits would go out to? 1, 2, 4, 8, 16, 32. So if I wanted to know that number, what would I add? 1, so I'd say 1, 2, 4, 8, 1, 2, 4, 8, 16, 16, 32. And then I would just do what? Now I know this is going to be an odd number. Why do I know it's an odd number? And then I would add these up, and that would come up, and that would give me the decimal equivalent, which would be 63. But this is the way we'd count, guys. We count just like we do in decimals. So I start off with 0. And then I go 1, 2, 3, 4, 5, 6, 7, 8, 9. I've run out of combinations and I want to keep counting. What do? You put a 1 up there and you put that right there. And then you start repeating, right? You understand? So notice this does the same thing. 1, 0. I've run out of combinations. What do? Put a 1 and add a 0. Then I count. I've run out of combinations. What do? Add a 1, 2 zeros. Then I keep counting. I run out of combinations. What do? I add another digit, start counting from here. So it's the same way, right? Y'all understand? Yes or no? Okay, so I'm going to go over, how many combinations do I have in base 2? 2. Okay, so I've run out of combinations. What do I need to do? I add another one, put a 0 up there, and start counting. Okay, so I've run out of combinations. What do? And add 2 zeros. Then now I can go 1, 0, 1. I can go 1, 1, 0. Then I go 1, 1, 1. I've run out of combinations. What do? added 1 and start over, right? You understand? Then my next one would be what? 1, 0, 0, 1, right? Then I'd go 1, 0, 1, 0. Then I'd go 1, 0, 1, 1. And then I'd go 1, 1, 0, 0. And then I'd go what? 1, 1, 0, 1. Then I'd go 1, 1, 1, 0. And I'd go 1, 1, 1, 1. I run out of combinations. What do? Add a 0. And that's the same thing you're going to do. That's the same thing you do in base 10, right? Exactly the same thing. But here we've only got 2 combinations, right? So if you look, that's what we're doing. 0, 1, run out of combinations, add a 0. This would be 2, 3, 4, 5, 6, 7. That's the decimal equivalent. This would be 8, which is what I put up a while ago, right? If you remember, I threw that number up there and I say, what do y'all see it as? And everybody's, it's 1,000. Until I come over and do what? 2. And that's why we have to understand that if I write numbers now, from now on, you have to know what base it is. Because by default, our brain is going to see things as what? As decimal. By default, your brain is going to see things as decimal. So that's why I'll subscript every number. Or it'll be in a column that says, convert the following decimal numbers over to binary, right? But if I just write a number up here, I'm going to let you know what base this is. And we would keep going. So here I've run out of combinations. What would I do? I'd add another 0. I add a 1 and just start over. And then I go through these combinations all the way from here till I get up to there, and then I'll do what? Yeah, it's just like it, but once you run out of combinations, you do what? You add another digit, then you start over with your 0. Okay. So all we went up to was 63 here. But notice all your even numbers, no matter where I pick up, all your even numbers, this guy right here is going to always be a what? 0. And all your odd numbers, this is going to be a 1. Now, what I'm telling you, and I think I've made this point, just because you come up with an odd number for an odd decimal number don't mean it's right. But you know, if you start off with an odd decimal number and you end up with an even binary number, you know it's got to be what? Wrong. You need to go back and figure out where you went wrong. Odds are you forgot to subtract the power of 2 or something like that. So adding, this guy gives you a bunch of rules, but all we're doing is adding 1s and 0s, guys. So what's 1 plus 1? Okay, so that's going to be 0 with a carry 1. It's a 2. Huh? 1 plus 1 is 2. Right? Oh, this is subtraction. I'm on the wrong side. So this is 1 plus 1 is what? 2. That's going to be 0 with a carry 1. So in fact, that's what you. And this is some people. So here I'm writing down. Here I'm writing down a number. Now, what's nice about this in decimal, you might have up to a carry of 9, right? You understand? But here, the only thing we're going to ever carry is what? All we're going to do is carry a 1, right? You understand? So it's like me, you know, if I come over here and all you're doing is writing down the number. So what would this be? If this is base 10, what would that be? 9. This right here. 3 plus 4.
Oh, you add?
No, we're adding. I'm over here, guys. I'm just right. So what's 3 plus 4?
7.
Okay, 7. Okay, what's 9 plus this?
14.
Okay, so what I'm doing is I'm writing down 14, but I'm writing 14 like that. So that'd be 4 with a carry 1. But still, that's what? That's 14, right? 1, 4, 14. Right? You understand? Okay. What's a binary 2? That's a binary 2, right? You understand? Okay. Y'all understand? This is a binary 2. If that's a binary 2. 1, 0 is a binary 2. So 1, 0 is the base. So what would I do right here? I'd say 2, but all I'm doing is writing the 12, but I'm carrying the 1 over to the next column, right? You understand? Yes or no?
No.
So 1, 5, 9, 3. Okay. 6, 5, 4. Okay. So what's 3 plus 4? What's 9 plus 5? 14. 14. We say it's a carry of 1, but all we're doing is writing the number. Since we're over 9, we're just writing the other digit up above the other character. You see what I'm talking about? That's 14. Okay. And this right here would be what? So there's the 12 right there, right? You understand? So this is a binary 2. So over here I say, okay, 1 plus 1 is a binary 2. 1 plus 1 is a binary 2. 1 plus 1 plus 1 is a binary 3. 1 plus 1 is a binary 2. This would be a 1. This would be a 1. And that's the answer. So what's nice about this is you're either going to add 0 plus 0 is 0. 1 plus 0 is 1. And then 1 plus 1 is a 2. And you carry on what? You carry on the base. So on decimal, what do we borrow? We borrow tens, right? So what are we going to borrow in base 2? What are we going to borrow in base 2? Okay. So let's subtract this. So 1 minus 1 is what? 0. 1 minus 0 is 1. 1 minus 1 is 0. 0 minus 0 is what? 1 minus 1 is 0. 1 minus 1 is 0. 1 minus 0 minus 1. I'm going to borrow 2. So in decimal, you borrow what? You borrow tens, right? In binary, we borrow what? 2. And all you got, guys, is you're either going to subtract 1 from 1 or 1 from 0. Is that harder than base 10? It is that easy. So to me, binary math is a heck of a lot easier. So to me, binary math is a heck of a lot easier than decimal math.
So this is in base 2 when you're subtracting that.
These are all base 2, yeah. See, it's labeled up here.
You subtract 2.
We borrow a 2. What do you mean? We don't subtract 2, we borrow a 2.
Borrow, yeah, borrow 2, and then 1 from 2 is 1.
You better not come up with a 2 down here. If you come up with a 2 down here, it means you what?
When the other was washed out, it was 0, 0.
What's that? I'm listening.
Oh, so, I was asking about how you getting that, the base 2.
Anywhere along,
I'm listening.
How you getting the base 2?
Because it says it's binary right there. It says adding and subtracting what? Binary.
or could you give me an example of one of these problems where, let's say at the top there, where you got 1, 0,
Sure. Well, what we'll do is, what I'm gonna do is I'm gonna exit out of this,
that's all right.
and I'm gonna come up here and I'm gonna bring up a blank slide.
I was just wondering,
And what do you want to do? Give me.
somewhere along there, I wanted another one where you got to borrow in the middle of it.
Sure. We'll come over here. In fact, we'll come over here and do this. So I will do this one.
You're gonna borrow 2.
So what do I borrow? I borrow here 2. Borrow from that makes this a 1, makes this a 2. Borrow from that makes this a 1, makes this a 2. Borrow from that makes this a 1, makes this a 2. Borrow from that makes this a 1, makes this a 2. Borrow from that makes this 1, makes this a 2. Borrow from that makes this right? Then I come over here, makes this a 2. So it'd be 1, 1, 1, 1, 1, 1, 1, and these are base 2 numbers. So you do just like you do like you do in decimal. So I borrow a 10. If I got to borrow, I'll mark this off and reduce it by 1, right? You understand? So in decimal, we borrow 10s. So if I had 100, if I had 100 base 10 minus 1 base 10, then what do? You borrow from this, makes it a 0, makes this a 10. Now, normally we do this in our head. Then what do? We mark this out, borrow this, makes this a 9, makes this a what? A 10. Borrows out, makes this a 9, makes this a 10. And that's the way we do the math. So this would be 999, right? You understand that? Now, normally what I do is I just pop 1s up there. So normally what do y'all do on that? You'll just put 9s up there, right? You understand?
So how would you know the base?
What I do to make sure that you understand what base I'm dealing with is I'm going to put a little subscript right
No,
here.
I know that, but I'm saying if we were to determine the base, how would we be able to determine the base if it's not given?
Well, exactly right. You said that was $100 question. If the base is not given, you're going to assume right off the bat it's base 10. And that's why I am going to always specify the base. And that's a perfect example. If I just threw a number up here, even if it's got 1s in it, right? Y'all understand that? So if I come over here and do this, then you know it's what? Base 8. So you're exactly right. Now up here, I didn't put it because what did they say up there at the top? Yeah, it said adding and subtracting binary numbers. So, but when I throw a number up there that it's not already defined what it is, I'm gonna let you know. Which one? This one? Okay, 1 plus 1. I'm just writing down a 3, guys. See that? That's a 3. This would be 0 with a carry 1. This would be 1. This would be 1. This would be 0 with a carry 1. I need to take that 0 out so y'all don't get confused.
So, anything.
So what do y'all want to add? Just give me some 1s. So we got this is base 2. What do y'all want to do? Y'all want to add them or subtract them? We can subtract them. I can tell this number up here is bigger than that number because of that bit right there, or that digit right there. So we want to add them. Okay. So let's do this in a different color so y'all can make sure y'all see this. 1 plus 1, 0 with a carry of 1. 0 with a carry of 1. 1 with a carry of 1. 1. 0 with a carry of 1. 0 with a carry of 1. 1 with a carry of 1. You just write down a 2. You just write down a 2.
So, that 1 plus 1.
Where's 1 plus 1?
The first all the way to the beginning.
This one right here.
Yeah. So that'd be
1 plus 1 is equal to 2.
okay.
Right?
Then
Which would be a 0 with a carry of 1.
why are we carrying?
Because that would be like me saying 9 plus 9, and I write down 8, and you're asking me, why are you carrying a 1? Right? You understand? Right?
You gonna always carry 1 with you.
And the 2 way plate.
Well, here's a 3.
Whenever it's 0, one got to go in front of the period. You said 2 way plate.
I didn't mean to erase all that, guys. I know some of y'all was writing it down. I didn't do it. Don't get mad at me. No. Because 0 is considered to be an even number. You can't say that. So so this is 1. Okay, so this is binary, right? You understand? So this is 1, 2. So this would equal to a 2. This would equal to a 3. Okay. So I'm gonna come up here and I'll write down a number so we can subtract it too. Okay. So I can't, when I come over here and do decimal, let's say 19 plus 19. Okay, now the biggest number I can represent right there, the biggest number I can represent down there is a what? Is a 9. But I come up and get a what? 8. It's what? But it's 18, which is 8 with a carry of 1. Okay, you understand? So the biggest thing I can represent down here is a 1. So anytime I get over a 1, anytime I add and get over a 1, I have to carry. Okay, right, you understand. So if I say, you can't say that because now that's not legal binary. Okay, you understand. So this comes up to be 2. Well, what's a 2? There's a 2 right there. So all I'm doing is just writing that. So what did I do? I wrote down my 18 like this, right? You understand? I took the carry and wrote it up there. Even if it came up to be 28, I would carry the 2 and put the 8 down here, right? You understand? So this is a 2. And all I'm doing is writing down the 2. But how am I writing down the 2? In binary. How am I writing the 2 in binary? How would I write a 2 in binary? And there it is. That's 2, right? You understand? See, that's 1, 2. Okay, and this is 1 and 1. That's 2. Okay, now this is a 3. Well, there's a 3 right there. So what I'm going to do? 1 with a carry 1. Or you just say 3, right? Okay. And this would be 0. 1, 1. This with a what? With a carry 1. This is 0 with a carry 1. This would be 0 with a carry 1. This would be 0 with a carry 1. Now this is a 3. This is a 3. Right? You understand? So what's a 3? Well, that's a 3 right there in binary. That's 1 and 2. That's a 3 in binary. All I'm doing is writing down a 3, but I'm putting my other digit up there. And then here I would just write down a 2. Just like if I had 9 plus 9, I wouldn't say this is 8 with a carry of 1 because we assume that to be a 0. I just wrote down the 18, right? So up here I just wrote down the what? The 2.
Would you, when you get through that, subtract that number from?
Sure, I'll subtract. That's why I made sure the bottom number was less than the top number.
I wasn't sure.
Okay, guys. So let's subtract them. By the way, this is not going to be on any test.
Oh, yes, but it's set.
So if you don't get it, then don't worry about it. I don't think there's any subtraction. Is there any math on lab 3? Yeah, it's on the slide because it's in the textbook. So what's 1? I'm going to subtract them now. These are base 2. What's 1 minus 1? Okay. Here, I got to borrow, but this is base 2. So in decimal, you borrow 10s, right? In binary, we're going to borrow 2s. So I got to borrow. I'm going to mark this out. Makes this a what? A 0. I'm going to borrow a what? A 2. What's 2 minus 1? 1. Okay. Oh my goodness. Here I got a 0 minus 1. What do I have to borrow? Mark this out. I decrease it by 1 just like you do in decimal. But here when we decrease it by 1, it's always going to go what? 0. And it's gonna make this a what? A 2. 2 minus 1 is 1. 0 minus 0 is 0. I can't subtract this. What do I have to do? Borrow a what? A 2. 2 minus 1 is 1. 0 minus 0 is 0. Can't subtract this. I have to borrow what? 0. Borrow what? A 2. Okay. Have to borrow this. What? I mark this out. I'm sorry. Mark this out. Make this a 0. Make this a what? A 2. 0, 0, 0. And there's our answer. If we converted these suckers to decimal, I guarantee you this would be the right answer.
That's what I wanted to see, because the other subtraction, where you borrowed was way down on the end.
But now what I was trying to show you that it's still the same way. Except, but decimal, what's nice about binary is that you're not going to borrow from a 9. You're not going to borrow a 10 from a 9. You're going to borrow a 2 from a 1. I mean, you're just going to decrease it by 0. So basically, it's, to me, adding and subtracting in binary is a lot easier than adding and subtracting in decimal. Even collimated numbers, even numbers, and a student figured this out for me. When we get into multiplication, we'll get into column. I mean, into more rows. And guys, y'all don't have to. And like I said, this is not going to be on the test. So if you don't really understand it, but you can understand the power and how easy it would be to design a circuit, instead of my circuit trying to recognize 10 combinations, it's only got to recognize 2, right? So a binary adder and a binary subtractor, these are very simple circuits. Now, it takes a lot of individual little circuits, but the circuits themselves are so simple. Don't worry about this. So so what I'm going to do for every pair of 1s, I'm going to carry a number of them. So I'm going to come up here and count. So this would be 3. I know that's going to be 1 with a carry. Yeah, I added. It would be real. The way you would subtract, you would basically do it 1 digit at a time. And we learned this when we came up and learned how to do. Originally, when the microprocessor first came out, the microprocessor could only do 2 math operations. And the only 2 math operations it could do was add and subtract. So how did we make it divide? We had to write a program to make it divide. And how did we do square roots? We had to write a program, so we had to learn all these little tricks so we could come up and do the program. So this would be what? This is 3. 1, 2, 3. I know that. Now, what I would do here, I'd go 1, 2, 3, 4, 5. How many pairs do I have? Okay, so I'm going to put a 2 up there, and then since it's an odd number, I'll write down there. Then I'd say 2, 3, 4, 5. 2 pairs. So what I do is I carry the number of pairs, and if it comes to be odd, I leave the 1 down there. Then I would go 2, 3, 4. That'd be 0, right? No, it's 4. It had 2 pairs, right? Then I'd go 2, 3, 4, 5, 6, and I'd write down a 6. And I'm through. And see whether you learned the trick or not, but if that was 5 digits of decimal numbers, even some of us would have problems, right? You understand? But binary, it's very easy to come up with an algorithm or a step-by-step process to do this math. Multiply, divide. So this would be an example of what I would run into if I was multiplying, right? So what I do is I carry for every pair. I just count the number of 1s, 1, 2, 3, 4, 5. If I've got an odd number, I put a 1 and carry the number of pairs. And if I could add these together and come up and get the right answer. But it's very simple. Once you learn the tricks, it's very simple math. It's a lot. And think about what you went through to learn decimal math. How did you learn multiplication? Yeah, flashcards, right? You understand. So So multiplication, what would I do? So what I've got is I've got 1 times 1, or I've got 1 times 0. So what would this be? What's 1 times 1? Then I take this through, right? So what's 1 times 1? 1 times 1. 1 times 0. 1 times 0. Oh, 1 times 1. Duh. Then what would I do? Yeah, I'd shift it over since it's a 0. I could shift it over too, or I could come in and fill it with 0. Some people like to do that, but back in math, you learn just to shift it over double, right? And then I'd move over this, and I don't even have to do that. All I got to do is just write down the number. I don't even have to look at it. I don't have to do the math. I'll just write down the number because it's what? Yeah. If I can write it down right. 111, Rich. Thank you. And then what would I do? I skip over this one, go over 2 spots right over here, and then do what? And then of course this would be this. Then I'd go 1 plus 0, right? Then I'd come up and say what? 1 1 0 0. This would be 0. This would be 1 with a carry 1. 1 with a carry 1 1 1. I did that right. But this is not something. But what I want you to understand, in binary math, we're either multiplying by what? 1 or 0. And we shift it over, the same thing would be true. But all I got to do now is learn how to add column numbers that's got multiple rows in it. And the circuits that would do this would be what? The circuits that do it would be very simple. Now this division, it's real hard. So can this go into that? Okay. Okay. Can this go into that? Okay. Can this go into that? How many times? If you say it goes in there 2 times, you know you what? Yeah.
But you have to put a 1 in front of those 2 zeros, right?
No, because it goes 0 times. In fact, I wouldn't even put those zeros up there, to tell you the truth, because they have no way. Then I write this down. Then I do what? Subtract it. What am I going to come up and get? So then I put a 0 there and a 0 there, and I'm through, right? Now, whether you fully understand it, you can see you don't even have to look at the weight of the number. All you're trying to see if the pattern is bigger. And it's obvious when a binary pattern is bigger.
What if 0 was a parity check? They have value to it in.
If what zeros are a parity check?
The one you said had no value. What was the parity check?
The one that has no value.
0 at the
These.
above the 1. Yeah.
Well, the parity is not part of the number. The parity bit is stripped off. So if I was to come over here and do this would be the number, and if I'm doing odd parity, then that would be what? 1, 2, 3, 4, 5. That would be odd parity. I put a 0 there. This 0 is stripped off. It has no weight. So what we're doing is the circuitry that checks to see if the error is correct or not correct. If it's correct or not correct, it's just dropped. You have to realize when you do that, I'm not going to stop instantly, right? Okay. So I have to get through my thought. So if I was to come up here and use even parity, 1, 2, 3, 4, 5, 6, right? Then that would be the parity bit. And then once I check parity, that bit right there is gone. We wouldn't do math with that bit. We wouldn't do anything, right? What we do in the receiving circuit that's checking for parity, once it's checked and said the parity is either okay or not okay, that bit is gone. So yeah, it wouldn't be anything. So what would I do if I was doing parity? I would add another what over here? I'd add another bit that has no value to the weight of the number. Okay. It's strictly in there for what? Checking. Okay, guys, y'all go ahead and take a break.
I hope it's like when you start.
Yeah, if I ain't gonna
Everybody come in with like.
please everything. Yeah, they can have it.
Right.
You're right.
Yeah.
On our test method, it's gonna be everything in chapter 1 through 3.
Except for the repetitive addition stuff.
Nothing
mean,
special,
sorry. Huh?
nothing special that we need to worry about, nothing special that we need to focus on.
No, I'll put a review out there.
Okay, so we're gonna have a review on
Yeah, I'll give you a written review, said this is what you need to know for the test.
it. Okay.
If you know that, you're fine. If you don't know that, you're not fine.
I got you. That's what I wanted to get at. I was like, there was a lot in chapter 1 through 3, but I was just trying to see on what focus, you know what I'm saying, because we didn't go over a lot there. It's fine there.
Now, and we're about ready to start labs too. And then after this, we'll be probably in lab more than we are in class. I know this is really a lot. I put a written review up there. It says, you need to know this, you need to know this, you need to know this. This will be up on the Blackboard site. Under test review.
That's what we were just talking about. She never had you before, and I thought, well,
So I always put
no,
on.
you know what I thought? I said, you got to know everything. Everything.
We had one of the guys, Joe Bear Preston, I don't know. He went to 4 interviews at 4 different companies, and he said there was not a question they asked him that we haven't covered in class. And he got on at Honda, by the way. He decided to move to Lincoln. But not a single, he said there was not a single question for Joe Bear. Did you have a question with Joe Bear? Preston. He's the guy that was he's in the Army Reserve. He keeps his hair cropped real stuff. Wears glasses. Joe Bear's been around when he graduated this last time. No, that was his name. It's Joe Burt, but I forgot where it comes from. It's got the exclamation mark on it. So it's pronounced Joe Bear. He let me get by with Joe Burt for a long time. And then he sent me an email with his name hyphenated.
Well, that's the whole point. Graduate, go to work, do a job, start over.
But that's what he said. He said we give out a lot of information, but it's information that you never know what they're going to ask you on the interview.
Yeah,
and all it takes is one wrong answer. So we had a guy, when we replaced Brittany LeGrand, she was our instructor, decided that teaching was too much. So this is some terms we need to understand, guys. So in a binary, every digit is called a what? Bit. Groups of 4 consecutive binary bits, so you just can't pick them out. They got to be in consecutive order. We refer to this as what? Nibble. I think that the person who set this up must have been hungry when they were coming up with all this. Then a group of 8 consecutive binary bits, we refer to this as a what? Byte, and then we lose, they must not have been hungry anymore. A group of 16 binary bits, from the least significant bit, we refer to this as a what? Word. A group of 32 binary bits, we call that a long word. I've never seen it called a long word in PLCs. In PLCs, they refer to it as a double word. In computers, they'll call it a long word. And in PLCs, they call that a double word. And then a group of 64 consecutive binary bits, we refer to this as a quad word, but in PLCs, they call it a double long word. Now, most PLCs usually give up on this because this is something around 2 keys. So normally in industry, we don't have to count that far. But some of them do support these quad words. So if you're in your computers, then these would be the guys you look for if you're in the PLC and these guys. So we'll differentiate and show you how you define those.
Is this one,
Don't know, but I don't think it's in the textbook. But this is something you need to know because you're going to hear this all the time. And unfortunately, so memory in computers for a long time has been organized in bytes. But we've lost that term. So it used to be 8 gigabytes. Now people say what? 8 gigs. And they have no idea what gigs is, right? So it's actually, so it still is. So everything, and this is going to make a difference. So when the PLC deals with numbers, it's going to limit the numbers to a certain number of bits. And so that's what we're going to have to understand is what's going on here. So when we say this number the biggest number I can possibly have is 65,536, then we'll know why, and I'll explain why, because that's 16 bits. That's the biggest number you can represent with 16 bits. And then we're going to get into signed numbers, and then it's going to have fun with that. So y'all got these down. We'll use it. You'll hear this all the time. You'll hear this in PLCs all the time. Least significant bit. Counting from the least significant bit. Good question. Even though it was on a previous slide, but I didn't say anything about it. I think we flew through that one.
I lost my page on the computer.
Hexadecimal, we're not going to teach this in years. So hexadecimal, if I was going to convert a big decimal number into decimal, I'd pick up my calculator. I wouldn't, because you got to divide by 16, and then you keep up with, then your remainder is going to be a fraction. You'd have to take the fraction and multiply it by 16 to come up with your whole number. So doing the way the book teaches is very, very hard. And we don't use hexadecimal. We use hexadecimal to represent large binary numbers. So what we're going to find out is extremely easy. Once you learn the trick, it's extremely easy to go between hexadecimal and binary hexadecimal. And also octal. Octal was the first base they went to represent large binary numbers. So PLCs are going to support four things. They're going to support decimal, they're going to support binary, they're going to support hexadecimal, and octal. Those are the 4 number systems they recognize. And if you take advanced PLCs, we can tell you how to, by default, the PLC is going to assume when you enter numbers in, it's going to assume they're decimal and it's going to do the conversion for you. So if you don't use it, if you don't enter number in the decimal number systems, you have to tell the PLC it is not a decimal number. So in this class, guys, as far as when we're not going to do any math in this class. In lab, we're going to get up through counters. But we're going to have to understand what sets the range of the counters and what does this, and we'll talk about that. So hexadecimal, we count starting with what? 0. And then when we get up to 10, how do we represent a decimal 10 in hexadecimal? Use the word what? Use the word A. This would be 11. This would represent 11. C would represent a what? 12. 13, 14, and 15, and then we run out of combinations. So let's count in hexadecimal. So I'd start off with what? We start off with 0, by the way. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What do I need next? A, B, C, D, E, and F. I've run out of combinations. What do I do? I put a 1 out here and start with 0 again. Right? And that equals 16. If I convert 1 0 and base 16, that's 16. So 1 0, that magic combination of numbers always equals to the base. Then I'd go 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 1 7, 1 8, 1 9. What comes next? And 1A, 1B, 1C, 1D, 1E, 1F, 2 0, which is equal to 32. If I converted that over, that's 32. Then I just keep going. 2 1, 2 2, 2 3, 2 4, 2 5. Of course, what people want to do, they get to 19, they want to say 20. In fact, 20 is we're not supposed to say 20. We're supposed to say this 2 0, the way you're supposed to say it. But just about everybody will call it 20, right? Even though it's technically it's not 20. 2 5, 2 6, 2 7, 2 8, 2 9. What comes next? 2A, 2B, 2C, 2C. Usually say when I say 2B, I say 2C, 2D, 2 what? E, 2F, 3, 0. And I would keep going until I got up to F. Right? You understand? Then I'd go to what? 1, 0, 0 and start the whole thing over again. Until I got all the way up to what? F. Then I do what? I add another 0 and start the whole thing over. And I keep counting. So that's why we count in X. That's F. It's what's FFF? It's 48,767. I don't know. It's 48. Huh?
What is it, like 15 times 15 times 15?
No, it would be, what we would do, technically, if I was going to go to base 10, first thing I'm going to do is I'm going to get everything into base 10. So if I was going to convert this without a calculator, guys, and you've got a 16 multiplication table on your powers chart, right? So what I would do is I would come over here. This would be F. This would be 16 to the 0, 16 to the first, 16 to the second, which means nothing. So what I'm going to do to get this to decimal, I'm going to convert everything into decimal. So I'm going to, instead of putting, so what this would be is, what's 16 to the 0? 1. What's 16 to the first? What's 16 squared? Look it up on your chart. 256, right? 256. Okay. Then what I'm going to do, I'm going to say this is going to be F, which is what equal to, what's F equal to? 15 times 256. Plus, what's F? 15 times 16 plus 15. And then I would add all that, I would multiply that out and add them up and come up with my decimal number. I knew it was 4. I was going my power. I knew it was one less than 4,090. I was trying to do it, one less than 4,096. So that's nice to know, right? But it gets very, very cumbersome. So even I would probably know this, even though I screwed up. I would probably know it because I know it's all ones, and I would go to the next higher power of 2, which would be 4,096, and I'd subtract 1 from it. Do you need to know that? No. But I'm showing you how you would do it, right? You understand? So we're going all the way back to what I learned in base 10, and I'm just putting everything in decimal, right? You understand? Everybody okay? So you're going to have some hex numbers on your lab. I'll show you how to do that a lot easier. So if I was going to go between, so I'm gonna just to show you something. Let's say I have A, B, 9 or 99, and then I come up here and I'd say, okay, this would be 1, this would be 16, this would be 256. So down here I'd say A times 256 plus 16 times, oh, I'm sorry. Now I wrote that backwards. Let me keep it in the same order so I don't mess you up. 9 times 16. And by the way, A99, that's an odd number, so I should expect my decimal number to be 9. I mean odd plus 9. So what do we come up and get? Yeah, 10. I'm sorry. Thank you, Terrence. So that's not A, that's 10. I need to get it all in binary. Okay, 2 what? 713. Okay. It has a chance of being right because my hex number is, my hexadecimal number is, okay. Okay, now watch this. So basically you had to have a calculator to do that, right? What I'm going to do is I'm going to write down this right here. This is base 2. And I'm going to go 1, 2, 4, 8, 16, 32, 64, 128. Let me spread it out, guys, so we can do this. I'm going to show you. I'm going to show you. But I'm going to show you how easy it is. So if I was going to convert a hexadecimal number to decimal, I would convert it to binary. Because then I'm dealing with addition and I'm not dealing with a calculator, right? You understand? So I'm going to spread this out. And guys, and it's not a trick. It's mathematical. It's mathematical. So A, 9, 9. So if you took this and you did 1, 2, 4, 8, that's 2 and 8. What's that? 10, which is what an A is. Okay. So what I'm going to do now is I'm going to drop back. And I'm going to just write 1, 2, 4, 8, 16. And I'll go and then we'll add them up and see if we come up and get that same answer. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. Did I skip one? Okay. 1, 2, 4, 8, 16, 32, 64, 128, 256. So we got a problem with this right here. Y'all sure that's right? Oh, I'm sorry. This is 2048. Okay, so let's add 2048. Everybody can do this without a calculator, right? Plus 512, plus 128, plus 16, plus 9. Add those up and see if it don't come up to be 2,713. If it don't, then, huh? Okay. So I took that in my head without using a calculator and I converted that to binary just like that. And here I did all this math. I multiplied 10. Of course, that was an easy number, but you can see going from using powers of 16, I would have to use a calculator. Going through binary, you shouldn't use a calculator because it's just basic base 10 math, right? You understand that? So I could take this number, I could take a big old number, and I could come up here and I can divide by 16, keep up with the remainder. So then my remainder is not going to be a 0.5 anymore. It might be a certain weird number. Then I would have to multiply it by 16 to get my whole number, so I know what to write down over in my remainder column. That's the way the book teaches it. What I would do is I would go through binary. So what I'm going to do now is I'm going to show you exactly how to go between binary and hexadecimal. So how many combinations, and there's a little formula that we can use to determine how many combinations we can represent with any base digit. So if I use hexadecimal, then each digit can have 16 combinations, right? I need to write smaller. I need to get all these on 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. Is everybody okay there? Okay. So if I use 4 bits of binary, this is a number. So to calculate the number of combinations you can have with any base given the number of digits, You take the base and raise it to the number of combinations. So 4 bits of binary would give me exactly 16 combinations. How many combinations do I have with base 16? 16 combinations. They're exactly the same. If it works out the same, then what I can do is I can use 4 bits of binary to represent each one of these digits. So 0 would be represented with that right there in binary. This would be 1. This would be 2, 3, 4, 5, 6, 7, 8, 9. There should be a chart on your book, right? Yeah, 9, A, B, C, D, E, and F. Now I got it. So I can write down any hex number, C, D, 3, 9, and all I'm going to do is, you can't drop any zeros, guys, is I'm going to write down the 4-bit pattern that represents those. So what's a C? Look it up on your chart. 1, 0, 0. Then I write down the code for a D, right? Oops, messed up. D. Then I write down the 3-bit pattern for a 3, and then I write, or the 4-bit pattern for a 3, and then I write down the 4-bit pattern for a 9, and I'm through. If we converted those in base 16 to base 10, we'd find out that those numbers are exactly equal. So to go between binary and hexadecimal, or vice versa, you got to memorize 16 patterns. You don't even have to. You can do 1, 2, 4, 8 if you want to. And I talk about when you're in elementary school, you know, multiplication is just repetitive addition. So 5 times 5 is actually 5 plus 5 plus 5 plus 5. But instead of you writing that out a long time, you learn multiplication tables. Huh? You learn multiplication tables, right? You understand that? And how far did y'all go with those multiplication tables? 12, yeah. Here you got how many combinations? 16 combinations that you would have to know. That's it. 16 combinations. So if I had a big old large binary number and I wanted to give it to you, how many of y'all could get this right? Okay, what I'm going to do is I'm going to take the number and I'm going to split it up into groups of 4s. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. If it don't work out, you can add a 0 to the right. To the left. You can't add a 0 to the right, right? To get a pattern. What's this a pattern for? A. What's this a pattern for? D. What's the pattern for? 6. What's this a pattern for? B. What's this a pattern for? I've converted that over. So what would be easier if I was calling out numbers to you? 1 0 1 0 1 1 0 1 0 1 1 0 1 0 1 1 0 0 1 1. Who would have wrote that down right? But if I'd have said A, same speed, A, D, 6, B, 3, how many of y'all wrote that down? Okay. So if I'm going to convey large binary numbers to you, would you rather me do it in binary or another base that makes it easier? So base 16. And this is base 16 and base 8 is the same way. Base 8 we use groups of 3s, and base 16 we use groups of 4s. So this is as far as we'll go. So this is it, guys. I mean, if I was going to go from hexadecimal, if I was going to go from binary, if I was going to go from hexadecimal and I needed to go to decimal, this is what I would do. I would go to binary, and then I'd write down my what? 1, 2, 4, 8, 60, 32, 164, 128, 66, 512. 1024, 4096, and I would do what? Then I would add them. That's the way I would do it.
Like say, you take groups of three,
They say you use groups of three.
same thing.
Opta we use groups of three, hexadecimal we use. Okay?
That's all I heard.
All right, guys, see y'all Monday.
It says Monday. Okay, so we'll just study everything that's happening.
So do you have like a study guide?
Yes, I do. I'll put it, it'll be on Blackboard under test review.
Is it all gonna be on the, laptop, or we're gonna have like a paper portion and a laptop?
And this test is all on computer.
All
I'm pretty sure, let me look, no.
It says what now?
on the computer.
No, I think the numbering system conversion is not, because there's so many ways you can go wrong, right?
We can keep that, so there will be a second, you this on the test.
Yes.
Test when?
And like I said, this guy's, I know this is a lot of regard, so yeah, you'll use that on every test.
Okay, cool. Okay,
Test.
You said it's gonna be on
Yeah,
the.
it's on the weekend, boy. For real, that. You need to come on.